Let's very briefly recap the concept of channel length modulation, and then we'll get into transconductance and all that kind of good stuff like we intended to. Wrapping up our review of how MOSFETs operate. And then we will get into simple amplifiers. We'll have that portion wrapped up. So, channel length modulation. So when a MOSFET device is operating in the saturation region, which we define to be VGS greater than VTH, meaning that we have caused the conditions for strong inversion to occur, and VDS is greater than or equal to VGS minus VTH. The channel formed beneath the gate inches off. And so stylized look at this would be something like this. Here we have our P substrate, field oxide layer. Let's make this longer so that I can make the channel long enough to look at. Here's our body connection. It's going to be P plus. Here is our source connection. That'll be N plus. Over here is our drain connection. Here's our poly gate. And let's just say our body connection is at ground. Our source connection is at ground. VG is greater than VTH. And over here, VD is greater than VG minus VTH, where I'm leaving off all my S's because the source is obviously at 0. So it doesn't, we're not having to worry about that real potential difference there, right? So what our expectation is here is that our channel is pinched off like so, where let's define this distance as L. This is the positive X direction, okay? So what we talked about in class on, today's Wednesday, so this would have been Monday, was simply we took the drain current ID to be 1/2 mu n C ox W over L times VGS minus VTH quantity squared. Effectively, we made an assumption based on the math that says that the drain current should be independent of the drain source voltage whenever the device is operating under saturation conditions. Realistically, though, this is not the case, because as we increase the drain voltage, the location of our pinch off point moves more towards the source. So I'm going to do this one in blue. And we'll have this guy right here effectively be a length that we're going to call L prime. Okay. So because the physical location of the pinch-off point in the channel is dependent on our drain source voltage VDS. The device current ID cannot truly be independent of the voltage VDS. So effectively, from a mathematical perspective, we are screwing up the boundaries of our integration. Okay. What this manifests itself as is a change in the relative length of the channel. And as the relative length of the channel gets smaller, we should expect the current to increase slightly. And this is a fairly linear relationship. So instead, our device current depends on a channel length modulation coefficient and in my notes from the textbook for this class, they use capital gamma. But I want to say that in 335 and 336, I used lambda. So the reason that they don't use lambda in our textbook is because lambda was being used for the scaling factor of the process technology node. Okay. To be consistent with the previous classes that I've taught that uses this material, we're going to use lambda. And if lambda has units of the inverse of volts, we're dealing with a channel length modulation coefficient. And if it has units of length, it's obviously a scaling factor. Hopefully that's not too ambiguous, but I just want to make a note here. This is the symbol for our CLM coefficient, and I'll have to go back through and figure out some other thing later on. But anyway, so our device current is better represented as 1/2 mu n Z ox W over L times VGS minus VTH squared times 1 plus lambda VDS. I want to make sure this is a capital voltage here. Okay. Where lambda represents the relative variation in length for a given VDS value. So what this means effectively is that if I have a long channel device and my drain source voltage exceeds my gate source, or exceeds VGS minus VTH by some amount, okay? If my channel length is very long, increasing that VDS voltage is not going to change the effective length of the channel very much. But for a very short channel device, that same change in VDS could cause a large change in the effective channel length. So for long channel devices, we should expect lambda to be very small to the point of being negligible. And for short channel devices, we could expect it to be as high as 0.2 or 0.3, so that it adds some appreciable amount of increased current, okay? So this is something that we're going to have to pay attention to. What is interesting-ish about this particular parameter, though, is that in a process run, it's defined only for your smallest transistor size. So for a C5 run, your lambda value is usually given for a 10x2 transistor. So if you actually made a device that was, say, 20x4, the actual channel length modulation coefficient should be smaller because the length is larger, but it's pulling that same lambda value for everything. So from a design perspective, we have to pay attention. We're typically going to overestimate the effects of channel length modulation in our designs, even if we have longer length devices, just because of it being a constant value effectively for that process run, where it's really only truly representative of the smallest size of transistor that you're expected to implement in there. All right, so channel length modulation is going to play a big role in our small signal model that we're going to talk about in a couple of minutes. But before we do that, we're talking about transconductance. Small signal model note. No, it doesn't matter. I can draw it from memory. All right, so transconductance. A transistor's transconductance is a measure of the device's ability to generate a drain current in response to a gate voltage, or mathematically, our transconductance parameter GM is the derivative of the drain current with respect to our gate source voltage while holding our drain source voltage to be a constant value. Okay. So using this definition, we can find that our transconductance for a MOSFET transistor is given by mu n Cox W over L times VDS for our triode. I'm not spelling triode correctly. Operation defined when VGS is greater than VTH and VDS is less than or equal to VGS minus VTH. And it comes out to be GM is equal to mu n Cox W over L times VGS minus VTH for saturation. We're going to look at this before we introduce a couple of different ways to look at this real quick. We're reminding you here briefly that saturation occurs when VGS is greater than VTH and VDS is greater than VGS minus VTH. So which of these two quantities in the triode region or the saturation region, which one do we expect to be larger? So they both have a common factor of mu n Cox W over L, right? So obviously those are all constants, and so that bit is the same for both of them. So which one is going to be larger depends on how VDS compares to the quantity VGS minus VTH, right? So in the triode region, we know for sure that VDS has to be less than VGS minus VTH, which means the transconductance in the triode region is always going to be smaller. Has to be, okay? Why this is important is the transconductance effectively is in some ways a measure of how good our device is going to perform as an amplifier, okay? We are concerned about analog electronic circuits and using transistors as amplifiers. We want to make sure that we get the highest conversion of input gate voltage to output drain current as possible. And to facilitate that, we have to make sure that all of our devices will operate in the saturation region, because that's where we get the biggest conversion of input voltage to output current to occur, okay? So this guy right here, specifically our saturation mode equation, is going to be one of the most important things that we have to look at for determining our device's parameters. Now, depending on what information is known, we can develop a couple of alternative relationships here really briefly. This is going to be the same thing as 2 mu n Cox W over L times our drain current, or twice our drain current divided by VGS minus VTH. There are also other relationships that we could use that include the effects of channel length modulation, but we are not going to bother with those too much. The reason being is that the transconductance of our device depends on the DC operating point of the system, and channel length modulation effects largely are not going to have a large influence on the DC operating point, but much more so on the AC operating point, or the amplification operating point of the system. So we're not throwing away a ton of information by calculating GM specifically using DC operating point values, and then only bringing the effects of channel length modulation into account when we're looking at things from a small signal amplifier perspective. In the long run, it's just going to mean less math. And we are just trying to figure out kind of how these things behave anyway, since this is all based on Boltzmann statistics. We never know exactly how the thing is going to behave to begin with. So this is giving us a good approximation of our behavior. So another thing that we need to take into account sometimes, specifically with integrated circuits, is the concept of body effect transconductance. So since our transconductance, our general transconductance, depends on the quantity VTH, and the threshold voltage is dependent on whether or not body effects are present, it stands to reason that our transconductance also has some relationship to our body source voltage, VBS. So our body effects transconductance, GMB, is defined as the change in drain current with respect to the body's source, excuse me, this should be BS voltage, which is given by mu n C ox W over L VGS minus VTH times partial derivative of our threshold voltage with respect to our body source voltage. If we were to take the partial derivative of our threshold voltage with respect to our body source voltage, and recognizing that this is just negative of the partial derivative of our threshold voltage with respect to our source body voltage, effectively I can change my subscript by including a negative sign. This is simply going to be negative 1/2 gamma, our body effect parameter, times our contact potential plus our source body voltage to the 1/2 power, yielding a body effect transconductance that is our normal transconductance times gamma over 2 times the square root of 2 phi f plus VSB. I need to go back so you guys, yeah. No, not a problem at all. I realized after the fact that I let you guys look at that for about 2 seconds before I changed the page. So try to jerk. All right. So now we're going to introduce our small signal model. Here's our gate terminal. This section down here is going to be our source terminal. And then we have our transconductance, GM, multiplied by our gate source voltage, VGS. And what that dependent current source is doing is effectively telling us how we change convert some AC gate source voltage into a current flowing through our drain at the output of the device. So I'm going to call this resistance right here where this is defined to be delta PDS with respect to ID. So this is how our chain link modulation manifests in our small signal model. This is just 1 over lambda ID, where ID is our DC operating point of our transistor. And I'm going to extend this over here like so. Talk about that in a second. Here is our drain. And then we also have this source body voltage. Actually, sorry. Just for the sake of space, I'm going to need to move this definition elsewhere. So let's call that R naught is equal to BDS over ID is 1 over lambda ID. My body effect transconductance. Notice that the direction is different, is GMB, VSB, like so, where this is my body terminal. Then I have gate source voltage up here. Yes. And one thing that I want to point out about this particular small signal model is that we are assuming our device is operating in the midband, so that all of our internal capacitances of our device are effectively looking like open circuits, right? So if we wanted to have a more accurate depiction, we would also need to include a capacitance CGS between our gate and our source, a capacitance CGD between our gate and our drain, a capacitance CSB between our source and our body, and a capacitance here CDB between our drain and our body. We'll revisit some of the frequency stuff that we did in 336 in this class as we talk about concepts like frequency compensation when we're dealing with multi-stage amplifiers and all that kind of stuff. But we are not going to hit these capacitors again for a little bit here. But when we're dealing with effectively the frequency response of our amplifiers, obviously they're going to come back into play. Okay. So this is the small signal model that we are going to deal with when body effects aren't present. Effectively, GMB VSB is going to look like an open circuit because the source body voltage will be 0. And so there will be literally just a short circuit between those two terminals. All right, so that's all the background that we supposedly need. Now, let us review simple MOSFET amplifier circuits. So the first one that we're going to look at is our common source amplifier, which from a discrete level design looks something like this. So here's VDD. We have some drain resistance RD. We have some biasing resistance R1. Another biasing resistance R2. Our source will be tied directly to ground. And then we would have to capacitively couple our input signal to our DC biasing circuit, like so. To measure some output voltage as a function of time here. So if we wanted to find our small signal parameters, we would need to first calculate the DC operating point of the device. So our large signal model would look something like this. So in our large signal model, we are going to short circuit our small signal input voltage, and all of our capacitors should look like, our coupling capacitors should look like an open circuit. So effectively, we would have this guy right here, VDD. Here's our resistance RD. Here's R1. Here's R2. Ground and ground. Here is our large signal drain current. And then over here, this open circuit represents our capacitor. Here's RG. And then our input signal would be shorted. So this is our gate terminal, this is our drain terminal, and this is our source terminal. What can we say effectively by inspection here? Well, we know that our gate terminal voltage, VG, is effectively determined simply by a voltage divider relationship, right? So that's going to look like VDD times R2 over R1 plus R2. Our drain voltage, VD, so this is the voltage at this node right here. It's just our power supply voltage minus ID times RD. And our source voltage by inspection is 0 volts because we're tied directly to ground. From this, we can say that ID is 1/2 mu n Cox W over L VGS minus VTH quantity squared, where we are assuming that our circuit is operating in saturation and channel length modulation effects are negligible. Negligible to the DC behavior of the circuit. So just by gleaning those different things about what the various voltages have to be dependent on our parameter, we can effectively solve this system in a pretty straightforward fashion and know what all of our voltages are at the various points. And then from here, we can get into our small signal model, okay? So our small signal model, let's see, let's do it on the next page because I don't have a lot of space. And let's call this an AC model. So for our small signal model, we have to turn off all of our DC sources and leave all of our AC sources on, right? So we'll start, we're also going to assume that the excitation frequency is such that our gate capacitance CG looks like a short circuit. So effectively, we're going to have something like this. Here's our resistance RD. This is our output node. This is our small signal output voltage Vout. Here's R1. Here's R2. This is shorted. Here's our source resistance RS. Here's our input signal Vn of T. And so I'm using this drawing to effectively make sure that I know where all the parts that are going to go into the true small signal model are. But I will go ahead and list our assumptions up here. Frequency of Vn of T must be high enough such that the impedance of our capacitor CG is approximately 0 ohms. So redrawing this in a way that'll be a little bit better for our analysis, we would have something like this. Here's our gate terminal. Here's our source terminal. Here's our small signal voltage VGS. Here is GM VGS, and it's like I'm running out of room here. Here's R naught. Here's RD. Here's our drain. This voltage here, where our output voltage is measured. Where GM is given by 2 mu n C ox W over L times ID. And R naught is 1 over lambda. So what level of design goes into this? Okay. So what I mean by that specifically is if we look at this drawing right here, right? So our output voltage, V out, is going to be given by negative GM VGS times R naught in parallel with RD, just using Ohm's law. So to be clear, for, I know it's been several months since we've looked at this. Effectively, since this node is at ground and this node is at ground, I'm tying those two resistors together. And my current is flowing into the negative polarity terminal of those two resistors, because effectively what I'm saying is that V out is this voltage. Okay. So one thing that we could observe here is that since R naught and RD are always in parallel, if we want a large voltage gain, RD needs to be as close to R naught as possible. That's one thing that we can glean from this, because the parallel combination of RD and R naught is only going to be at best as large as R naught over 2. If RD is smaller than R naught, it will be smaller than that. Okay. Another thing that we could potentially maximize here is the quantity VGS. That may be slightly less obvious, but the voltage VGS here is defined by a voltage divider network, right? So since VS is obviously 0, because our source is tied to ground, our voltage VGS is our input voltage as a function of time multiplied by R1 in parallel with R2 over RG plus R1 in parallel with R2. If we want all of our input signal to actually be amplified by this thing, what does that necessitate? R1 in parallel with R2 needs to be much larger than our gate resistance. Otherwise, we are truncating the signal that we are applying to be amplified. Okay. We can tie these two quantities together and say that our voltage gain for this system V out over V in is going to be negative GM R naught in parallel with RD times R1 in parallel with R2 over RG plus R1 in parallel R2. Okay, so this is what the realization of a discrete common source amplifier might look like. What do you think an integrated circuit common source amplifier might look like? Anybody have any thoughts?
Instead of just being R1, R2, this should be poly as well.
So one thing that's interesting about integrated circuit amplifiers is that typically speaking, we don't use capacitive coupling to put our input signals on there. We would actually supply a DC voltage with an AC voltage superimposed on top of it so that we don't have to worry about that biasing stuff there. Not to say that we can't capacitively couple or anything like that, but it's typically not done, okay? So instead, what we would most likely see would be something like this. We would have our power supply voltage, this guy right here would be V bias 1 plus Vn. And then here is where we would measure our output voltage. So effectively, the biasing portion of our previous network, which is really just the signal chain of VDD R1 in series with R2, is taken care of by just applying a DC voltage. And then we superimpose our AC signal on top of that. The role of the resistor RD is now being played by this PMOS transistor, okay? So how is that going to change things? For the DC operating point, effectively what this guy up here is doing is playing the role of a current source that is forcing some amount of current to flow down through our transistor. Let's call this one M1 and this guy M2, right? I'm calling it a current source because we have a constant voltage VSG here, which means transistor M2 is operating with some constant amount of drain current that's flowing through our signal, right? So we'll have some drain current ID flowing here, and then that same current, drain current ID, has to be flowing through transistor M1. So that PMOS transistor on top is the thing that's establishing the DC operating point of this circuit from our small signal level. Okay. So our small signal analysis is going to look something like this. So I'm going to start by just doing the small signal model for the NMOS device. So here is our input voltage, the in, Those bias voltages look like short circuits to ground. Here is the gate of transistor 1. Here is the source of transistor 1. GM1, VGS1. This is our voltage, VGS1. Here's R01. And this is our drain for transistor 1, where we're measuring our output voltage. For transistor M2, we're going to have something similar. So here's GM2, VSG2, where we're changing the order of the subscripts there because in a PMOS transistor, the source is usually at the point of highest potential. Here is R02. This node right here is the drain of transistor 2. This node right here. Actually, let me, sorry, swap those. Here's the gate of 2. This is the source of 2, which is at ground. And then here is our voltage, VSG2, and the drains of the 2 transistors are tied together like so. So, Stephen, I'm going to pick on you just because you haven't seen this the most recently. What's VSG2? What's VS2? What's VG2?
Zero.
Yeah.
Well, it's all zero to zero.
Yeah, so because the source terminal of our PMOS transistor was tied to our DC power supply, and we're doing a small signal analysis, all of our DC voltages look like a short circuit to ground as we turn off those DC voltage sources, right? So since our source voltage is at a DC voltage and our gate voltage for our PMOS transistor is also at a DC voltage, then the quantity VSG2 at a small signal level looks like a short circuit or zero. So from that, this current source is supplying 0 amps of current, or effectively looks like an open circuit. So what does that, how does that make R02 look to transistor M1, the bottom half of the circuit? So R02 would be connected between those that common drain connection and to ground. So effectively R02 shows up in parallel with R01. And so we get a voltage gain that is simply negative GM1 R01 in parallel with R02. Arguably simpler to deal with than our previous equation. We just need to be careful about effectively superimposing our AC signal that we're amplifying on top of our DC voltage source. And then we also have to be careful about how we might go about implementing, from a design perspective, what we use to establish the DC operating point of our PMOS transistor. And so what I mean by that is that's usually a simple analog voltage divider style circuit, but we have to be very careful about variations in temperature, variations in power supply voltages, and all those kind of things. So we have to pay attention to exactly how those are going to be implemented, because let's say that our power supply voltage was 5 volts, and so we wanted the bias voltage to be 4.17 volts or something like that, because that gives us exactly 10 milliamps of current. We're making this thing behave like a 10 milliamp current source, right? So because a simple voltage divider circuit says, oh, it's going to behave this way to give us this exact thing, but as we take into effect temperature effects, as we take into effect power supply ripple and all that kind of stuff, we can't guarantee that we're getting exactly 10 milliamps out of this thing. And that's where we are going to have to start paying attention on how to do biasing that provides those things and provides that rigidity that we really need to ensure our device operation correctly. All right, so that's a simple one. This guy is effectively the building block of really 2 of the 3 stages of most op-amps. Okay, the common source amplifier effectively shows up or is mirrored in our differential input stage. And the common source amplifier is also usually used as the second gain stage after our compensation stage, which is just literally a resistor and a capacitor in series to provide a large amount of gain, to step our small gain from our differential stage up into a large gain. Okay. So this simple circuit of 2 transistors stacked on top of each other, 1 PMOS, 1 NMOS, is really a fundamental building block of op-amp design. All right, so let's now talk, let's stop. It's 1:35. We'll talk about common drain amplifiers and common source amplifiers on Friday.
Real quick, going back to read this is signal model.
Sure.
This is next